Hey everyone! Welcome back to RoboNinjaz. Today, we'll dive into an essential topic, push buttons with ESP32. We'll explore how to configure and program a button with the ESP32, understand pull-up and pull-down resistors, discuss button debouncing, and learn how to tackle debouncing using both hardware and software methods. The circuit. Alright, this is the circuit we'll be using. One terminal of the push button is connected to GPIO32, while the other is connected to ground. For more details about the push button, check out this video. I have connected the components according to the circuit. Now, we can write the code to read the switch in. Connect the ESP32 with a micro USB cable. Let's open Thonny, and you might see a message in the shell saying that the connection has been lost. To reconnect, simply click the stop button. Once reconnected, you will see the MicroPython REPL restored, and the file system will become visible again. If the REPL is not restored, press Ctrl+C multiple times immediately after pressing the stop button. This will interrupt any running code and bring back the MicroPython prompt. Make a new file, go to File New. Save the file, select MicroPython device and save as switch.py. Let's dive into the coding part. Let's check the code. First, import the pin module from the machine library. Then, configure GPIO32 as an input using pin. Start an infinite loop to continuously run the code. Read the pin's value and store it in a variable. The value will be 0 for 0 volt and 1 for 3.3 volts. Finally, print the stored pin value. It's time to run the code. Click the run icon and observe the output in the shell. But wait, something looks off. The zeros and ones are appearing randomly. This isn't right. Something went wrong. But don't worry, we'll fix this. Let me explain why this is happening. Consider this circuit. I have connected GPIO32 to 3.3 volts, so the value of GPIO32 will be 1 or high. Now, in this circuit, GPIO32 is connected to ground or 0 volt, so the value of the pin will be 0 or low. But what about this circuit? Here, the pin is not connected to either voltage levels. This leads to unpredictable behavior, where the pin randomly switches between high and low due to electrical noise. This pin state is called floating. This instability can cause false readings in your project. Pull up and pull down. To fix this issue, we can use a pull-up resistor or a pull-down resistor, depending on the requirement. This is the pull-up configuration. This is a current limiting resistor, which controls the amount of current flowing into the GPIO pin. In this case, a 10K resistor connected to 3.3 volt will limit the current to around 33 microamperes, calculated using Ohm's law. This small current is enough to keep the pin in a defined high state without damaging the ESP32. Similarly, this is the pull-down configuration. In this setup, a 10K resistor is connected between the GPIO pin and ground or 0 volt. The pull-down resistor gently pulls the pin down to 0 volt, preventing it from floating and ensuring a stable low state. Alright, let's go back to our circuit. In this circuit, the switch is connected to ground, so we need to add a pull-up resistor to keep the GPIO pin high when the switch is not pressed. There are two ways to do this. Use an external resistor, like a 10K ohm resistor connected to 3.3 volt, or use the internal pull-up resistor built into the ESP32. Let's go with the internal pull-up. It's simple and doesn't require any extra components. Stop the running code by clicking the stop button or pressing Ctrl+C. This will interrupt the program and bring back the REPL prompt in the shell. Now let's make a small change to the code. I've modified the pin setup to use pin.pull_up. This enables the internal pull-up resistor. Now run the code again. Yes! You'll see a stable high state, 1, in the shell. Try pressing the switch. Yes! It works! The value drops to 0 when the switch is pressed and returns to 1 when it's released. Let's take it a step further, modify the code so that when the switch is pressed, it prints pressed. It works! But, hold on. There's a problem. Button bounce effect. When we press the switch once, it prints pressed multiple times. This is caused by button bounce. Inside a mechanical switch, when you press it, two metal contacts come together. But they don't make a clean connection instantly, they bounce for a few milliseconds, creating quick spikes in the signal. Take a look at the graph. A shows the ideal switch press, a clean, instant transition. B shows the real-world behavior, a messy signal with rapid changes before it stabilizes. This is exactly what we need to fix with debouncing. Ready to solve it? Button debouncing. Debouncing can be done in two ways: hardware method and software method. This circuit demonstrates one of the hardware debouncing methods. A 0.1 microfarad capacitor is connected between the GPIO pin and ground. This capacitor acts as a filter, smoothing out the high-frequency ripples caused by the rapid contact bounces when the switch is pressed. As a result, it helps to reduce the bounce effect to a certain extent, making the signal more stable. There are also other hardware-based debouncing techniques, such as using SR latches to lock in a clean transition, or using dedicated debouncing IC like LS18, which are specially designed to clean up noisy switch signals. Now let's implement the software debouncing method. If you look closely at the graph, you'll notice that the spikes happen only during the transition, right when the switch is pressed or released. In the other areas, the voltage remains stable. So, to tackle this in code, we'll simply add a short delay right after we detect a switch press. This delay gives time for the bouncing to settle down. By the time the delay ends, the spikes are gone, and we can safely confirm the button press. Awesome! You've successfully implemented software debouncing. Now your ESP32 can reliably detect switch presses without getting confused by those nasty little bounces. It's a simple trick, but super effective, especially when you're dealing with mechanical components. So, all of that, and more, see you in the next video. Do like, share, and subscribe for more tech content.